most of the discussion that we have had in this course up till now applies primarily to linear polymers. So, when we talked about the various models for polymer chains, they were mostly restricted to linear polymers. Similarly, for solution thermodynamics, the development that we introduced using the Flory-Huggins theory, that was also using a model of linear polymers. So, in this week what we will do is discuss the case of branched polymers, primarily hyper branched polymers, as well as network polymers, and we will see how the behavior of these is different and how from linear polymers, and how that behavior can be described. So, for branched polymers we will study what is the effect of branching on, let us say, the number average degree of polymerization or the weight average degree of polymerization, and that will primarily be the focus of today's lecture. In the other lectures this week, we will also explore the concept of gelation in network polymers. So, how the formation of cross links leads to network polymers, and at what point a kind of gelation phenomenon occurs. These are the topics that we will be exploring this week. So, in today's lecture we will focus primarily on branching and the case of hyper branched polymers. So, we will just introduce the case of hyper branched polymers, and then talk a bit about the how one can calculate the number average degree of polymerization or the weight average degree of polymerization for the specific case of such hyper branched polymers. If we consider let us say monomeric unit, and let us represent that monomer by this A-R-B F minus 1. Here A and B are functional groups which are mutually reactive. So, we will be focusing primarily on branch or hyper branched polymers that form through what is called step polymerization or condensation polymerization. So, here A and B represent functional groups that are mutually reactive. So, A can react with B to form a link between the monomer units. But A and A cannot react. Similarly, B will not react with B. Now, if we consider this case where here again the R that we have, it just represents some other group that might be present in the monomeric unit, but that is not a functional group. So, it is not participating in the reaction as such, in the polymerization reaction. Now, if we look at this kind of a monomer ARBF minus 1, so it contains one A functional group, and it also contains F minus 1 functional groups of type B. Now, if F is equal, let us see what happens when F takes different values. So, if F is equal to 2, in that case we will have an ARB kind of polymer, because F minus 1 will be just 1. The monomer will have just one A functional group and one B functional group. So, when a polymerization reaction takes place for such monomers, then they will invariably lead to the formation of linear polymers. So, any monomer that is bifunctional, that its polymerization will result in the formation of linear polymers. But if instead we have a monomer where this quantity F, if this is greater than 2, in that case branching can occur, and we will get the formation of hyper branched polymers. The condition for formation of branched polymers is that this F that we have, it should be greater than 2, and if it is equal to 2, then we will just get linear polymers. If we want to just represent this schematically, then the monomer that we have, that can be represented something like this, where repeat units have been shown here, and the black dot or circle is any other group that might be present in the monomer, but which is not a functional group and which is not participating in the polymerization reaction. This monomer can react with another monomer and form this A-B linkage. Okay, so, we have said that A can only react with B, or B can react with A only. So, we can have a reaction between the A and B functional groups of two monomers, and we get this linkage. Similarly, as the reaction proceeds, we can, the B groups that we had on this monomeric unit, that also can react with other monomer, A groups of other monomers, and in this way we can have a formation of kind of a branched polymer. Okay. And if it proceeds further on, we will get a hyper branched polymer which will have a very high degree of branching. So, even for this simple case, we can see that we have branching over here as well as a small branch over here, or if we consider this to be the main chain, then instead this can be considered as a branch. So, in any case, if this reaction proceeds further, then we will have a polymer molecule that will be highly branched, and that basically can be referred to as a hyperbranched polymer. Let us look at how one can determine the number average degree of polymerization for such hyperbranched polymer formation. So, again we are considering the polymerization of a monomer which is of ARBF minus 1 type. So, it contains a single monomer molecule contains only one functional group of type A and F minus 1 functional groups of type B, where F has to be greater than 2. So, in the schematic that we had drawn in the previous slide, there F was equal to 3. So, that the monomers that we had were of ARB2 type. But the discussion that we will have and the theory that we develop, it will be valid for any kind of polymerization where this F it will be valid for any value of F in general. Okay. So, as we discussed, each monomer has one functional group of type A and F minus 1 of type B, and then now if we consider a case where the reaction has proceeded up to a certain point and certain number of functional groups have reacted. So, let us say that the reaction has proceeded up to a point where fraction of functional groups that of type B that have reacted, let us say that fraction is referred to as P. Let P represent the fraction of groups of type B that have reacted, okay. And let us say that initially in the reaction mixture we had n tot this number of monomers present. So, initially to start with we will have just a monomer molecules present, and once the reaction starts, then the functional groups will start reacting, and that is A and B, these groups will start reacting and start to form linkages between the monomeric units, and this will lead on to the formation of dimer, trimer and larger polymeric molecular species. So, if we are using this symbol P to represent the fraction of functional groups of type B that have reacted at a certain point, then using the fact that we had initially n tot number of monomers present, what we can say is that the number of groups of type B that have reacted, that is P times F minus 1 times n tot. Okay. So, how this comes about is, if we consider a single monomeric molecule, a single monomer molecule, then that contains F minus 1 functional groups of type B. Initially if we have n tot number of monomer molecules, then the number of functional groups of type B present will be n tot multiplied by this F minus 1. And if at a certain point a fraction of P of these functional groups of type B have reacted, then the number of groups that have reacted will be just this fraction P times the total number of groups of type B that were present initially. So, that will be P times F minus 1 n tot. And similarly, if the number of groups of type B that have reacted, that will be equal to the number of groups of type A that have reacted, because any reaction basically takes place between a group of type A and a group of type B. So, the number of groups of each type that have reacted at a certain point, they will be equal. So, that is why the number of groups of type A that have reacted at this point where the fraction of B groups reacted is P. So, that number will also be the same as what we have here, and that will also be P into F minus 1 into n tot. So, that is the number of A groups that has reacted, and initially if we have n tot number of monomers, we know that in the type of monomer that we are considering, each monomer molecule has only one group of type A. So, initially in the reaction mixture, the number of functional groups of type A present will also be simply n tot, and if the number of A groups that have reacted is given by this expression, then the number of groups or the fraction of A groups that has reacted will simply be whatever the number of groups of type A that have reacted divided by the total number of groups of type A that were present. So, this P f minus 1 times n tot divided by n tot. So, that fraction of A groups that have reacted will simply be P times f minus 1. And generally this quantity P that we have, which is representative of the fraction of B groups that have reacted, this quantity P is also referred to as the extent of reaction. Okay, so it's a measure of how far the reaction has proceeded, and it's also called the extent of reaction. So, if the fraction of A groups that have reacted is this, then the fraction of unreacted A groups, that will simply be 1 minus the reacted fraction. So, the fraction of reacted plus the fraction of unreacted groups of type A will simply be equal to 1. So, the fraction of unreacted A groups will be 1 minus this P times f minus 1, and since the total number of A groups present in the system is just equal to that number of monomers present initially, which is n dot. So, the number of unreacted A groups will get by just multiplying this fraction by n dot. So, that is what we have done here, and this is what we get. So, that is number of unreacted A groups. So, now we can identify a couple of things here. So, at any point of time during the reaction, if we consider the entire reaction mixture, it will consist of a collection of molecules of different sizes. So, at any point of time during the reaction, we might still have some unreacted monomer molecules present, as well as other molecules of different sizes present as well. But one thing in common about all these molecules will be that all of them will contain only one unreacted A group. So, whether it is a single monomer molecule or a large branch polymeric chain that has formed, in either case the number of unreacted A groups will simply be 1 per molecule. So, after identifying this fact, what we can say is that the number of molecules present at any point of time will simply be equal to the number of unreacted A groups that are present, because each molecule contains just one unreacted A group. That is what we have stated here, is that number of molecules present in the reaction mixture at any point of time where the extent of reaction is P, that will simply be equal to the number of functional groups of type A which are still unreacted. Okay. Again, using this condition, now what we can do is try to develop an expression for the number average degree of polymerization for this, such hyperbranched polymers. So, if you recall the number average degree of polymerization, that we had introduced in the very first lecture, and that is a measure of how many repeat units or monomeric units are basically present on average in a given polymer chain in a certain polymer sample. So, if a polymer sample is polydispersed and has chains of different lengths, then on an average given the number of monomeric units or the repeat units present in a certain polymer molecule, that is what this number average degree of polymerization represents. In the present case, what we can identify is that this number average degree of polymerization will simply be equal to the number of monomers that were present initially divided by the number of molecules that are present at any point of time in the reaction mixture. Okay. So, initially we will only have monomer molecules present, and as they start reacting, some monomers will convert to dimers, trimers and larger molecules, whereas some monomers will still remain unreacted, and as the reaction proceeds, more and more monomers will react and larger polymer chains will form. The number of molecules that have formed at any point of time during the reaction, if we take that number and use that to divide the number of monomers that were initially present, then that ratio basically gives the number average degree of polymerization. So, this is something that you can just consider a test case where, let us say, initially you had 10 monomeric molecules, and after a certain point of time you, let us say, end up with a system which has 2 unreacted monomer molecules, and also which has resulted in the formation of let us say 2 dimers and as well as a tetramer. So, initially let us say we have a collection of 4, 5, 6, 7, 8, 9, 10. So, initially let us say we have 10 monomer molecules present. So, that will be the numerator here, and of course, in a real system the number of monomer molecules will be huge, but just for as an illustration for a simple case, we are considering 10 monomer molecules. So, that will be the numerator, and at any point of time, let us say what we have is let us say 2 dimers have formed like this and 1 tetramer has also formed. So, we have 2 unreacted monomer molecules as well as these 2 dimers and 1 tetramer. So, that gives us the total number of molecules present at this point is simply 1, 2, 3, 4, 5. So, 2 monomer molecules which are unreacted, 2 dimers, that is 4 plus 1 tetramer. So, 5 molecules are present at this at a certain point of time when the reaction mixture has this composition. So, at this point of time the new denominator will simply be 5, and based on the ratio that we have 10 by 5, the number average degree of polymerization will simply be 2. And similarly, if the reaction proceeds further, so that at some other point of time, if the reaction mixture is such that we have a hexamer which contains 6 monomeric units and a tetramer. So, now the number of molecules present in the reaction mixture has reduced to 2, and initially the number of monomers was 10. So, now the number average degree of polymerization has increased to 5. So, just by looking at this case where this oligomeric species has 4 units and the other one has 6 monomeric units. So, on an average one would expect the number average degree of polymerization to be 5, and that is what we are getting from this relation as well. Okay. So, now we can use this relation and also the fact that the number of molecules present in the reaction mixture at any time, that is equal to the number of unreacted A groups. So, in the denominator that we have here, we can replace this by the number of unreacted A groups, and if we do that, the number of monomers initially present was n tot, that is what we have considered, and the number of molecules present in the reaction mixture, we have replaced that by the number of unreacted A groups present, and the expression for that we already discussed in the previous slide, that is this. So, that gives the number average degree of polymerization to be 1 over 1 minus p times f minus 1. Okay. So, this is a expression that is valid for a hyper branched polymer that forms where the value of f should be greater than 2. But even if the value value of f is 2, which will lead to the formation of linear polymers, even in that case this general expression is valid. So, for the case where let us say the value of f is 2 and we get linear polymers, so in that case this expression simply reduces to xn bar equal to 1 over 1 minus p, okay, for when f is 2. So, that equation for which is valid only for linear polymers, that is called the Carothers equation, and that was proposed long back probably in the 1930s by Carothers. A more generalized equation that is valid for branched polymers as well is this, where f can have a value greater than 2 as well. And in general, if f has a value greater than 2, only then one will get branched polymers and hyper branched polymers. So, now one thing to note here in this equation is that for a certain value of p, so for a certain value of this extent of reaction p, the xn bar actually tends to diverge. Okay. So, the xn bar or the number average degree of polymerization diverges when this p takes this critical threshold value of 1 over f minus 1. So, when the extent of reaction becomes equal to 1 over f minus 1, that corresponds to a point where this the expression that we have developed here diverges, and that essentially what that tells us is that the branching has reached to such a point that some kind of a gel formation or network formation resulting in gelation might begin. But that condition, this condition actually corresponds to the fact that the maximum possible fraction of B groups have already reacted. Okay, so the maximum possible fraction of B groups would have reacted when all the A groups present in the system have all reacted. So, when all the A groups are exhausted, the maximum number of B groups would also have been reacted, and beyond that no further reaction can take place. So, in general this point is not reached, and so gelation typically will not be observed for such a system, and will usually have hyper branched kind of polymers. development of this expression for xn bar that we have done here, we have used certain simple arguments and developed this expression, and it's fine. But if we want to extend this approach and try to find, let us say, the weight average degree of polymerization or the polydispersity index. So, if you want to find some certain other quantities related to the hyperbranch polymers. So, the simple approach that we have adopted here actually has its limitations and cannot be extended to obtaining other quantities like the weight average degree of polymerization. We will next discuss a more kind of more powerful approach, in the sense that it apart from giving us a number average degree of polymerization, it will also allow us to obtain the weight average degree of polymerization as well as the polydispersity index for a given hyperbranch polymer. So, this approach that we will be discussing next is a kind of a statistical approach, and for this discussion we will again consider, let us say, N-mer, which is basically a polymer which contains n number of monomer repeat units. So, we will consider the formation, we will start by considering the formation of a polymeric molecule which contains n number of monomer units, and we will refer to this polymeric molecule as N-mer. So, as we have discussed previously, the schematic that we have here, it contains, if we count here, it contains 10 monomeric units. So, this will correspond to a 10-mer. So, the expression that we will develop will be for a general case of an N-mer where the molecule contains n number of monomer units. Now, in this N-mer, for any N-mer that we have, the total number of B groups present will be F minus 1 times N. The reason for this is N-mer will contain single N-mer molecule will contain n number of monomer units, and each monomer unit contains F minus 1 functional groups of type B. So, that the total number of B groups present in an N-mer, that will be equal to just F minus 1 times N. So, for the case that we have here if we see the N, which is number of monomer units present in this N-mer, is 10, and the value of F for the monomeric unit that we have, it is a AB2 type of monomeric unit. So, the value of F is 3 for this case. So, the number of B groups present according to this formula will be 3 minus 2, which is 2 times 10. So, 20, and if we count here for this entire molecule, we will see that we have 20 functional groups of type B. Out of the B groups that are present in this particular N-mer, if we focus on the B groups that have reacted, so we are not talking about the reacted B groups in the entire reaction mixture, we are just talking about the number of reacted B groups in this particular N-mer molecule. So, that number of reacted B groups is simply n minus 1, because any N-mer molecule which contains n monomeric units will have n minus 1 AB bonds. So, each AB bond corresponds to the reaction between the functional group of type A with that of type B. N minus AB bonds basically correspond to the number of reacted B groups, and that can also be seen here, where since we have a 10-mer, so we will see that there are 9 AB bonds, 4, 5, 6, 7, 8, 9. Okay. So, those many B groups have reacted. So, all the B groups that are a part of these bonds, these are the ones that have reacted, and the remaining are of course unreacted. So, the number of unreacted B groups will be just the total number of B groups present minus the number of reacted B groups. So, that comes out to be this. And one more thing to note is that the probability that a B group has reacted, that is given by P. So, the extent of reaction that we have defined previously, the same P we are using here, and that P earlier had been defined as the fraction of B groups in the entire reaction mixture that have reacted at a certain point of time. So, now that fraction also is equivalent to the probability that a certain B group has reacted in the reaction mixture. So, if we just randomly select a B group and try to see if it has reacted or not in the reaction mixture, the probability that it has reacted at a certain point of time will simply be P, and and that same probability can be applied to for the reaction of all the B groups that are present in this N-mer. So, for any B group that is present in this N-mer, the probability that it has reacted is P, and the probability that let us say all the n minus 1 B groups that have reacted in this N-mer. So, the net probability that all of them have reacted is simply this P multiplied by itself n minus 1 number of times. So, that will just be P to the power n minus 1. Similarly, the number of B groups that have not reacted is given by this number here, and the probability that the B group has not reacted is given just by 1 minus P. So, the probability that a B group has reacted is P. So, 1 minus P will just represent the probability that a certain B group has not reacted. So, again the total number of unreacted B groups is this F minus 2 times n plus 1, and for a given N-mer, what we see is that it should contain n minus 1 reacted B groups and F minus 2 times n plus 1 unreacted B groups. So, the probability that n minus B reacted groups are present, that is P to the power n minus 1. Similarly, the probability that F minus 2 times n plus 1 number of B groups are unreacted will simply be this 1 minus P raised to the power that quantity F minus 2 n plus 1. The probability that this N-mer has formed will just be given by or will be proportional to the product of these two quantities, the probability that the n minus 1 B groups have reacted and the probability that the other B groups in the N-mer have not reacted. So, if we combine take the product of these probabilities, that will give us a measure of the probability that an N-mer has formed in the reaction mixture, and this probability that N-mer has formed in the reaction mixture is simply equal to the number fraction of N-mers that are present in the reaction mixture. Okay. And this number fraction is equivalent to the mole fraction as well. So, for a certain polymer molecule having n number of monomer units, the probability that it has formed, that is given by this expression here, and that is equivalent to the number fraction of such n-mer polymeric molecules present in the entire reaction mixture, and it will also be equivalent to the mole fraction of these n-mers in the entire reaction mixture. So, we said that the product of these two the two probabilities is actually a measure of this number fraction that we have, and because this extra term a n also actually comes in here. So, apart from the product of these two probability that will lead to the formation of this N-mer, that will give the probability of formation of this N-mer. This extra a n term appears because even when an N-mer forms, there are many different ways in which these n monomeric units can be arranged to get different arrangements of the same N-mer. Okay. So, this a n actually takes into account that extra number of arrangements that are possible for these n repeat units or monomeric units to get different let us say different arrangements of the same N-mer molecule. So, this a n also we can evaluate. So, what we need to do is take the product of the several of these terms, okay, and what each of these terms we will just discuss briefly, and we will see that this product which comes out to be this ratio, that is actually related to this a n here, the number of ways in which we can arrange this n monomer units to form our N-mer. Here, if we this expression that we have is based on the fact that the number of different ways of arranging the n monomer units to form the N-mer is basically equal to the number of different ways in which the respective or successive B groups can be chosen whose reaction with an A group will lead to the growth and formation of this N-mer. So, the first term here basically represents the number of ways in which a B group can be chosen for the first reaction and the first AB linkage to form. So, we have n minus 1 linkages here for the entire N-mer. So, for the N-mer to form, the first linkage that forms, the number of ways in which we can select the B group that takes part in this linkage formation, that is just F minus 1 times n, because that is the total number of B groups that are present for us in this monomer N-mer molecule. So, now that we have chosen that one B group out of all the B groups present and that bond AB bond has formed, for the formation of next AB bond again we will see how many different ways are there in which we can select an unreacted B group. So, one B group has already reacted. So, the number of B groups that are available for the formation of second AB linkage is given by just this term, which is F minus 1 N minus 1, because 1 has already reacted to form the previous AB linkage. Similarly, for the third AB linkage, the number of B groups available for selection is Fn minus 1 N times N minus 2. And if we go on in this direction, in this way, then the total number of reacted B groups is N minus 1. So, this the last term that we get, if you continue this series, the last term that we will get will be F minus 1 N minus N minus 2. So, that is the number of ways in which a B group can be chosen to form the last AB linkage for this N-mer. So, the product of all the different ways in which we can choose the successive B groups to form the AB linkages, that product is given by this expression, and that product is actually can be used to find out this AN. Okay. So, that the overall product that we have, the number of different ways that we have counted, that is given by this ratio, and but in this ratio that we have obtained here, some extra counting has been done, because all the different N monomeric units present which we are attaching to form this N-mer, they are indistinguishable, they are identical molecules. Their internal permutation actually will not lead to any distinct or distinguishable arrangement of a different N-mer molecule. So, we need to scale or divide this quantity that we have obtained by n factorial to account for the extra counting that has been done. So, this AN simply is equal to this term here divided or scaled by the n factorial term, which takes care of the fact that all the n monomer molecules that are being arranged to form this N-mer, they are identical. So, their internal rearrangement will not lead to a distinct or different conformation of our N-mer branched polymer. So, with this expression for AN, we can write the overall expression for this number fraction of N-mers as simply this here. So, this AN we have substituted here, and this is the expression that we get. So, now starting from this expression, which is the number fraction of N-mers that is present at a certain point of time in the reaction mixture when the extent of reaction is P. So, starting from this expression, we can next try and derive the expressions for the number average molar mass and number average degree of polymerization and the weight average degree of polymerization. And we will see that the number average degree of polymerization expression that we get is the same as what we already obtained using another approach, but using the current approach we can get other quantities as well. This is just the expression that we obtained, we have just obtained. What we can identify is that this number fraction of N-mers, okay, that number fraction, if we sum these number fraction over all the possible N-mers that might be present. So, if we sum it over n ranging from 1 to infinity, so starting from monomeric species molecules that are present at a certain point of time in the reaction mixture to very long let us say polymeric chains that are formed. So, if we sum over all the cases possible, then the number, since this is a number fraction, the overall sum should equal to 1. So, it's a normalized kind of distribution of the number fractions. So, using this fact that the number fraction, their sum over all the possible N-mers that can be present is 1. So, using the fact that this summation is 1 because it's a summation of number fractions, we can write down that this summation also is 1 because this number fraction is simply given by this expression here. So, now in this summation what we can do is take out the term 1 minus p over p. So, if we do that, we have taken out this term 1 minus p over p. So, in here actually this p to the power n minus 1 that we had, that changes to p to the power n, because if we take this p inside the summation, then this p to the power n will become p to the power n minus 1 here. Similarly, this the plus 1 in the exponent of this 1 minus p, that has been removed here, and that 1 minus p has been taken out here. And since the summation is over n, it's the quantity p does not depend on the summation index n, so it can easily be taken outside. So, just by rearrangement, what we can say is that the summation of this term, which is a n times p to the power n times 1 minus p to the power f minus 2n, the summation of this from n equal to 1 to infinity, that is simply given by this ratio p over 1 minus p. So, now that we have identified this expression, there is some substitution that we can make. So, what we can see here is that this p and 1 minus p to the power f minus 2 both are raised to the power n in this term. So, if we simply replace this quantity p times 1 minus p to the power f minus 2 by this symbol x, then we can write this expression in a kind of shorter format, and the equivalent expression will simply be this, where we have we have replaced this term simply by x, and that is raised to the power n. And before we move on to actually developing the expressions for the number average and weight average molar mass, there is a mathematical identity or mathematical operation that we will just discuss quickly, and which will be useful in further development of this theory. The mathematical operation that or identity that we are discussing is that if we have a summation of this kind, n to the power k a n x to the power n summed from 1 to infinity, then that equivalently can also be written as x times partial derivative with respect to x of this entire quantity, where we have changed this n to the power k to the n to the power k minus 1. Okay. So, if we instead of x, if we just replace x by what it stands for, then that expression becomes this. And here, instead of del by del x, in the next step what we have done is taken del by del p, and then to account for that change in the variable with respect to which we are differentiating, we have also multiplied this del p del x term here. We will see that the expression that we have developed here will be useful in developing expressions for both the weight average and number average degree of polymerization. So, the same expression that we had in the previous slide has again been written here. Okay. And let us consider a case where this quantity k is equal to 1. So, for that case, this summation n into a n into x to the power n, that simply becomes this term, where if we take k equal to 1, then n to the power k minus 1, that term simply becomes 1. So, now let us see if we can obtain expressions for these two terms. We know from our previous discussion, just by using the fact that the number fraction, their sum is 1. So, from that we developed this expression that this summation is equal to p over 1 minus p. So, this we have already developed, and this equation here can be rewritten in this form, where we have substituted p over 1 minus p in place of this summation here. Okay. Next, if we try to carry out these two differentiations and substitute them back in this expression, then we will get an equation, a useful equation for this summation. So, x we have already defined as in terms of p as this. Now, del p del x one can write as del p del x is a term here, one can write as 1 over del x del p, and this since x is a function of p of this form, then that del x del p through differentiation one can evaluate, and upon simplifying that the expression obtained, finally we get this expression for del p del x. Similarly, for differentiation of the p over 1 minus p, that is an even simpler differentiation, and it upon differentiation we will simply get 1 over 1 minus p square. So, now if we substitute this expression here as well as 1 over 1 minus p square in place of this derivative, then finally this summation here will be given by p divided by 1 minus p times 1 minus p multiplied by f minus 1 as we have shown here. So, this equation that we have, this will be useful in determining an expression for the number average degree of polymerization. Again we have rewritten the expression that we obtained for the number fraction of an n-mer present, okay. And the number average degree of polymerization can simply be written as this n multiplied by this number fraction and the summation being taken from n equal to 1 to infinity. So, if we look at this carefully, this n is the number fraction which is nothing but the mole fraction. So, we discussed the number fraction is equivalent to the mole fraction of these n-mer polymeric molecules, and if we multiply that mole fraction or the number fraction by the corresponding number, and if we take the summation over all possible values of n, that's what that's a kind of a definition of the number average degree of polymerization. So, that's what we have used, and this kind of an expression, this is also called the first moment of this quantity NP. Again, by substituting this in place of NNP here, we get this summation, and that's the expression for xn bar, which is the number average degree of polymerization. Next, again as we did previously, we can take this 1 minus p over p outside, and that will change the these two terms in here. So, instead of p to the power n minus 1, we will have p now, p to the power n now, and instead this plus 1 here will not appear in this term anymore because that has come out here. So, now we have this expression, and we see that this term is nothing but again x to the power n. So, by identifying the fact that this term is simply x to the power n, we can write the previous summation in this form. This summation we have already in the previous slide obtained an expression for this, and that expression was this p over 1 minus p multiplied by 1 minus p times f minus 1. Since we have this value for this summation, so that can directly be substituted in this expression here, and that will give us an expression for xn bar. So, the expression for xn bar upon substitution is so this term we have substituted here. So, this 1 minus p will cancel this, p will cancel this. So, the final expression is this for xn bar, and we see this is the same as what we obtained earlier in the initial part of this lecture using a different approach. And for p, this is only applicable for p less than pc equal to 1 over f minus 1, because at p equal to pc this will diverge. Next, using a similar approach, we can also find out the weight average degree of polymerization. So, the good thing about this approach that we are following now is that apart from number average degree of polymerization, the weight average degree of polymerization can also be obtained. So, again we start with the expression for the number fraction of an n-mer that we have developed earlier, and the expression for x in terms of p, and we note that the weight average degree of polymerization is simply the ratio of this summation n square np by n np, and both summations are from n equal to 1 to infinity. So, this is something that we are not explicitly proving, but it can easily be shown. So, this np is simply given by this. So, if you substitute instead of nnp, if you substitute 1 minus p over p times a n x to the power n, then this 1 minus p over p will cancel in the numerator and the denominator here, and we will get this ratio of these two summations. Okay. And if you look at the denominator, this summation we have already developed an expression for this summation in the previous slide. Okay. Now, let us see how we can develop an expression for the summation in the numerator. Okay, and once we have both, we can just divide them and get an expression for x w bar. Again we go back to the general expression that we had earlier and use k equal to 2. So, for k equal to 2 we get n square here, and here we get n to the power k minus 1. So, in this case it becomes just n, and again other similar terms are there. So, this del p del x we have already discussed in the previous slide, that its value can be easily obtained, and the value is simply this, same as before. For this case, first we need to find out an expression for this summation, and then that expression can be differentiated with respect to p. Okay. So, now if we again note this term, this is nothing but again x to the power n, okay, provided that we are using this definition for x. So, and this whole summation is nothing but the summation that we have in the denominator here, and that summation we have already developed the expression for it in the previous slide. As we discussed, this term is simply x to the power n, and the value of this summation we have already discussed in the previous slide to be this. So, now this whole expression can be substituted here, and the partial derivative with respect to p can be taken. So, that this is a function of p and f, but since it is a partial derivative, f can be taken as constant, and then one can differentiate and obtain an entire expression for this term, and this del p del x is already known to be this. So, after doing these operations and combining all the terms, finally the expression for this this summation it can be shown to be simply this. So, now that we have an expression for this summation, which appears in the numerator here, and the expression for the summation in the denominator which is this one was already discussed in the previous slide. So, we can combine these to take their ratio to obtain the weight average degree of polymerization. So, the expression for weight average degree of polymerization we have again written here, and if you substitute the expressions for the two summations, one in the numerator and the other in the denominator, then what we see is this 1 minus p term will get cancelled. Similarly, this p will get cancelled here, and this will change this exponent here to 2. So, finally, the expression that we get for the weight average degree of polymerization is this, and we again see that this is also valid for p less than this p c equal to 1 over f minus 1, because at this value of p this expression also diverges. Okay. So, this weight average degree of polymerization is also valid for extent of reaction less than this p c, and from here we can easily obtain an expression for the polydispersity index, which is a ratio of the weight average molar mass to number average molar mass, and which can equivalently also be written as a ratio of the weight average degree of polymerization to the number average degree of polymerization. Okay. Because the weight average molar mass and weight average degree of polymerization, these two are just related by the molar mass of a monomer unit or a repeat unit. Similarly, these two are also related by the molar mass of a repeat unit. So, in going from here to here, that molar mass of the repeat unit will get cancelled, and we can just say that the polydispersity index can also be obtained as the ratio of the weight average degree of polymerization and the number average degree of polymerization. And if we substitute the two expressions that we have obtained for these, then and if we simplify, so this will cancel, change the exponent here to 1. So, ultimately we end up with this expression for the polydispersity index, and again this diverges at this value of p c. So, it is valid for p less than p c. Okay. So, that is the expression for polydispersity index, and we see that using the statistical approach we can apart from number average degree of polymerization, the weight average degree of polymerization and the polydispersity index, both we have been able to calculate. So, this approach or the statistical approach that we have discussed, it is a more powerful approach because it gives us more information about the system. Apart from these quantities, another important quantity that's different for a branched polymer compared to a linear polymer is something that relates to its size, and that's the radius of gyration. So, if we consider a randomly branched enmer which is ideal, so if we are neglecting again the excluded volume effects, then it can be shown, we will not go through a derivation here, but we will just write down the final result, is that this Rg square, the mean square radius of gyration, is equal to this quantity which is dependent on this f here, multiplied by b square n to the power half. So, this b is nothing but the size of the monomeric unit, and n, of course, if we are considering an n-mer, is the number of monomeric units. What we see here is that this Rg, if we just consider Rg and its how it scales with the number of monomeric units present in the in our n-mer for this branched polymer, randomly branched polymer, then it scales actually as n to the power 1 by 4, because this mean square Rg scales as square root of n. So, Rg itself will scale as n to the power 1 by 4, and this is in distinct contrast to the case of a linear ideal polymer, ideal chain, where Rg scales as n to the power half. So, this we have discussed earlier when we are talking about the chain models. So, for linear ideal chains, the radius of gyration scales as square root of n, whereas for this randomly branched n-mer, the radius of gyration scales as n to the power 1 by 4. So, what this illustrates is that the branched polymers have a smaller size than the corresponding linear polymers if both contain the same number of monomer units, and also the branched polymer actually scales more weakly, or the size of the branched polymer as quantified by its radius of gyration, it scales more weakly with the number of monomer units present compared to linear polymers. So, scaling here is n to the power 1 by 4, whereas for linear it is n to the power half. So, this illustrates that the branched polymers of the same number of units will be more compact in size, and their size will also scale more weakly with the number of monomeric units present. So, with that we will conclude our discussion of branching and branch formation of hyperbranched polymers, and how one can use the either statistical approach or a simpler approach to obtain quantities like the number average degree of polymerization, and specifically for the statistical approach also the other quantities like the weight average degree of polymerization and the polydispersity index. And in the next lecture we will consider the case where if cross links actually form between polymer chains, how that can result in the formation of polymer networks, and at what point this gelation, the phenomena of gelation basically takes place in such network polymers. Thank you.